Or maybe it was intended to be hard. I don't know. Oh, those 50 points are not. Oh, did I leave 50 points there?
Well, you said in the beginning how it would be switched, but like in there.
Oh, okay. Okay. Thank you. There's no telling what I've done this semester.
What happened? Oh, sorry.
Go ahead.
Okay, yeah. So like, I don't know. I didn't come up with a formula like it looks like you did. I just ended up. We worked on it long enough to where we found out pretty quickly that it would have to be, I guess, a permutation matrix or whatever. We found out pretty quickly it had to be completely ones, and that the signs didn't really matter. And so we kind of just played with it, and we eventually found two matrices that worked. But yeah, so we didn't really find like necessarily a. Oh man.
Oh, I think there are infinitely many answers to this which are reasonable. I mean, what is up to isomorphism the Langle sigma wrangle? What is that? I mean, it's Z3, right?
Yeah. Okay.
So unless I'm missing something here, you could I could find a faithful representation inside GL2 2R. I would just use rotations by how many degrees? 120 degrees, right? Rotation in the plane by 120 degrees. That's a 2 by 2 matrix. If you want to look at it that way, it'll cube to 1. That could give you a faithful representation of this thing, even inside GL2R. Making it GL4 is just allowing for this more lazy argument. In fact, you can see how to generalize this example to other groups, right? If you want to look at a permutation representation of a group, a representation of a permutation group, if you're looking at Sn, you can use n by n matrices, exactly what I did here, like thinking of E1 as being the one, moving the basis vectors just like I did. This is a trick. I would ask you guys if you have questions about the homework, which is due, but I'm afraid to. No? That's okay. What? You do?
No.
Oh, okay.
What happened in 2017? Like, you never talk about that class. We've never used any of their stuff. It's always 2016. Look what happens now.
Are you sure that you haven't done any of their stuff, though?
Yes.
Did you
And on your
say
website,
2016 was the first semester you ever taught abstract?
What's that?
Did you say 2016 was the first semester you ever taught abstract?
Yes.
Then we must have used I think the first test we had 2016 and 2017. I really do. I think we had two tests. I think we had 2017's test.
It must have only been the first test, though. It's on his website.
They keep giving us two to go off of. One of them was on the website he gave us. Like he posted two for us to use.
Let's see. Here's test 3 from 2017. See if anything looks familiar. Oh, look.
Oh, God.
There's one.
Hey!
Oh, my. Can we actually see that solution? No, I don't even want to look at it. I didn't.
Okay. Oh, I didn't add the MK in there. I didn't add that.
Okay.
I did have one.
This looks familiar.
Emily has a real question.
Oh, yeah? Go for it.
I don't know how to find site, like the inverse isomorphism for 72 to get my numbers back when I'm solving the quadratic.
So
I've done everything, I just need like site inverse.
let me get everyone up to speed with what you're talking about. So we're trying to find an isomorphism from H3.
I'm 72.
H3. Was it R cross C or C cross R?
R cross C.
R cross C. All right. So if you're looking for an isomorphism of algebras, there's some very nice things here. It's a linear transformation. that we're looking for. And so if we have a basis, 1j, j squared for H3, if you can tell me what psi of 1 is, and psi of j is, and psi of j squared is, fill in these 3 blanks, then you fix the map, right? But Liam, you can already tell me what psi of 1 is. But what is 1?
1, 1.
Very good. Right, where that's the complex one and the real one. And then the question is what's psi of j, right? So I would say what I encouraged Emily to look at was just like let psi of j be r comma z, and say you're looking for something that has r comma z cubed equal to 1 comma 1, right? So that gives us r cubed z cubed equal to 1 comma 1, which means we're trying to solve r cubed equal to 1 and z cubed equal to 1. But r cubed equal to 1 only gives us one real solution, namely 1. Stuck with that? Z cubed equal to 1. There are 3 solutions in the complex plane because it's a third order polynomial equation, which by the fundamental theorem of algebra has 3 zeros, possibly repeated, possibly complex. 2 of them are complex here. They're the conjugate pairs of the third principal root of unity, and it's conjugate. So the solutions to this guy, you can picture like so. Right? 1, let's call that thing omega, and this down here is omega squared. What is omega? E to the 2 pi I over 3. That is the complex number which cubed gives us 1. And more specifically, that's 2 pi over 3, right? Which makes this pi over 3, which makes this omega actually minus 1 plus I times the square root of 3 divided by 2. Explicitly, it's that. All right, so getting to the point, Emily would have had something like what, a times what, a plus b j plus c cj squared, yeah? Yeah. And that is going to be a times 1, 1 plus b times what? B times 1 omega, right? And plus c times what? 1 omega squared, right? And so, lo and behold, we have the formula a plus b plus c, and then a plus b omega plus c omega squared. Where omega is that, and omega squared is actually omega conjugate. Now, so the idea of that problem is what you do is you take the quadratic equation. Did you move the camera over here? Because the rest of them are going to be cursing you guys. So you take a quadratic equation in H3, right? We map it under psi to a quadratic equation in R cross C. Now, a quadratic equation in R cross C is easy to solve because it's a real quadratic paired with a complex quadratic, which we can solve by usual methods. So you solve it, and that gives you solutions in R cross C, which are pairs of reals and complex numbers. And then the cool thing is, if we can find psi inverse, that gets us back over here, which is the solution to the original problem. That's the idea here. Find the isomorphism, take the given equation, map it over to a corresponding equation in the isomorphic algebra, and then solve it using regular techniques, and then pull it back with the inverse map. But we need to find the inverse map, is what Emily's getting at. And so this is just, let's see here. So what we should do is we should set this equal to, let's say this is equal to R. No relation to the original r, okay? And let's say that this is equal to z. Right? Which perhaps we should write as x plus iy. So then psi inverse of r comma z is equal to a plus bj plus cj squared, right? Where a, b, and c are what? Ah! Well, I would say that a, b, and c, these are functions of r and z. Let me put it a different way. You're trying to solve, so what you're trying to do is you're trying to solve the following equations, Emily. You're trying to solve r is equal to a plus b plus c, right? And you're also trying to solve that x plus iy is equal to a plus b omega plus c omega squared. You're trying to solve these two equations. Solve for what? Solve for ABC, right? Once you've done that, you found the inverse map. And the second equation is a complex equation, so it'll probably be a good idea to look at the real component and the imaginary component of it separately, which is made possible because we know explicitly what omega and omega squared look like, right? Like omega squared is minus 1 minus I root 3 over 2. So this equation, here, let me just try, the real part of that equation is what? X is equal to A, and the B omega gives me what? Minus B over 2, right? And what's the C omega squared? Minus C over 2. That's the real part. What's the imaginary part? We got Y equals to what? There's no A. The B what? B root 3 over 2. Plus C root 3 over 2, right? No. Minus C root 3 over 2, right? Now we have three linear equations, real linear equations relating ABC and XYZ. Excuse me, RXY, right? So you can solve those. I would multiply that real equation by 2, and then I would add it to R. Then I don't know. Let me not do that. Don't trust me past this point. This is the big picture, though. Once you find that, then the rest of it it's not entirely trivial. This is not, if you didn't find it already, there's a reason for that. It's not an entire, it's not as easy as the isomorphism between the hyperbolic numbers and R cross R is like a much nicer, isomorphism to find. But they're all like this. You got to send one to one and send a generator to a generator, and the rest kind of falls out. So, there is two isomorphisms to use here, though, right? There's the one I wrote down, and what's the other one? The inverse? No, but...
Like A, B, and C to the 3 spots of that.
What I'm trying to get at is my choice of Z. I made Z equal to omega. What else could I have made Z equal to? Omega squared. Because really, H3 is the real group algebra of the cyclic group of order 3, and it has two generators, J or J squared. Because phi of 3 is 2 things. Or U3 is 1 and 2. So, All right, I digress. Does that help?
Yes.
All right. At least I did something productive. Oh my goodness, I'm going to be in trouble. I must go home.
Are you missing dinner?
Oh, I still need to. Oh.